Great. So welcome everyone to the third Zcash Show and Tell event. This series is about highlighting projects in the Zcash community and ecosystem. This presentation today comes from Jason Davies, who built an alternative zk-SNARK verifier for Zcash Sprout. It's written in pure Rust with a primary use for independently verifying the zero-knowledge proofs in the Zcash blockchain. So feel free to post any questions that you have during the presentation in the chat box on the side of the YouTube live stream on the channel. Or if you want to follow up afterwards, Jason's on the Zcash community chat, which is linked in the description. So now I'll just hand it off to Jason to start the presentation. Thanks for joining us.
Okay, thanks for the introduction. I'm just going to share my screen so you can see I've got some slides that I've prepared.
Yep.
So the title of my show and tell is Trust but Verify, which actually comes from an old Russian proverb, and it was popularized by Ronald Reagan in the context of nuclear disarmament. So this is about my recent work writing an independent zk-SNARK verifier for Zcash proofs. I wrote the verifier in Rust and then used it to independently verify all the proofs in the first 160,000 or so blocks in the blockchain. So what was the motivation for me to do this? Well, if you recall, back in summer 2016, before Zcash actually launched, they commissioned a whole load of external security audits of their code. And this included various experts, including NCC Group. And they released a very interesting report. And one of the points in their conclusion was that Zcash should consider implementing zk-SNARK proofs in a memory-safe language. The lib-SNARK code is one of the more vulnerable components in the Zcash daemon. While great effort has been made to sanitize untrusted data passed into the third-party library, memory safety issues are still an area of concern. And so really with the recommendation that maybe an implementation in Rust for memory safety would be a good idea. And essentially, if I was an attacker and I wanted to attack Zcash, obviously setting aside any serious issues with the protocol itself, the first place I would look is the actual implementation. I would look at the code itself. And one of the first things you kind of learn in security class is that nothing is truly secure, and you see all these statistics about the number of bugs per 1,000 lines of code and so on. So I would probably say that perhaps a third party, well, an external dependency like lib-SNARK could potentially be the first place you'd look, seeing as Zcash is based on the Bitcoin code base, which has been kind of around for quite a while now. And even though various issues have been found in Bitcoin and fixed over the years, you might look in somewhere that's maybe a bit newer and maybe some external piece of code that's fairly complicated. So lib-SNARK might be the place you would start for that. And here's a quote from Nathan Wilcox in one of the Zcash tickets, where he says that the verifier is a higher priority for security audit, since that defines consensus and is the easiest component for remote parties to supply malicious input to. So why would I want to implement it in Rust? Well, I've already mentioned memory safety, and if you're not familiar with Rust, Rust is actually it's a systems programming language that aims to have similar performance to something like idiomatic C++, but it emphasizes safety, and this means that in Rust code, you're completely prevented from making certain types of mistakes. So it's worth pointing out that actually you can mark certain sections of code as unsafe, and you can do things that the compiler would ordinarily prevent you from doing. but that makes it easier to audit the code that's marked as unsafe. But in the main, you're completely prevented from things like null pointers, dangling pointers, and even data races in multi-threaded areas. So one of the other things that Rust does as well is there are various runtime checks as well as compile time checks. So, for example, if you compile in debug mode, arithmetic has underflow checks. So potentially you could find bugs by compiling in debug mode and running a whole set of tests that potentially could trigger some kind of underflow. And finally, Rust is a good language to implement a verifier for Sprout, being as Zcash is already going in this direction for sapling. Sean Bow is writing a whole load of libraries for zk-SNARKs for sapling, which will use a new curve and so on. So I figured it would be useful to have a Rust version of the Sprout zk-SNARK stuff, starting with the verifier. So now I'm going to show you the actual Rust code itself. It's actually relatively simple when I actually got into it. So I went for the naive but correct option. So I didn't even implement any of the advanced optimizations in the more recent papers and the pre-computation steps and all of that stuff that libsnark does. I just wanted to, based on Sean's suggestion, he said, well, if you can make it look exactly like the code in the paper. So this is actually from the appendix in one of the recent papers, and you can kind of compare it. But I think anyone could compare this in about 30 seconds and check that it's doing the same thing. So it actually turned out to be easy. Obviously this depends on Sean Bow's work. He wrote a library called BN in Rust, and that's essentially an implementation of the curve BN254, which Zcash Sprout uses. So I don't know if you could see that on the previous slide, but here's kind of zoomed in version. Well, here I'm defining a few structs just to make it nice and clean for the Rust version. So this is the verifying key, and here's the proof, and they're defined in terms of various group elements, which I'm using from BN there. And then if we look at the actual verifier, this is essentially translating what's in the paper into Rust. So it's pretty straightforward. We have these 4 checks, well, actually 4 steps, I should say. Firstly, we can compute an accumulated input circuit. Secondly, we run the validity of knowledge commitments for A, B, and C checks. And then we, thirdly, check that the same coefficients are used. And then finally, we check for the QAP divisibility. So that's essentially the same as what's done here. And so I did that, and then I needed to obviously actually run this on the Zcash blockchain, seeing as that was the whole point of it. So then I had to hook up Rust to C++. So I'm going to show you another bit of the Rust code, which is the external interface that C++ talks to. So the easiest way for C++ to talk to Rust in this context, actually it made it slightly easier that Sean told me. The memory representation of group elements used by BN is exactly the same as libsnark. So in fact, we can pass in raw pointers, const pointers from C++, and then Rust can essentially access those bits of memory, and it's the same memory representation, so it can just access them as the BN group element types. So here's the rest of that function. Here's the body of the function, where this is where we actually have a bit of unsafe code, you can see here. And the reason that's marked as unsafe is because it's dereferencing these raw pointers. And there are various things that can go wrong with dereferencing raw pointers. For example, it could be that you've received a null pointer. So I actually do a couple of checks for those in there. So, and then we call this verifier finally at the bottom. The reason it's actually using uint8 is because there's no, as far as I can tell, there's no kind of easy rusty way to cast to a bool in a safe way. So I've just used uint8. So that's either a 1 or a 0, which is passed back. And this is the change that I made to the Zcash daemon. So I guess there's a couple of things to mention here. The first bit is that lib-SNARK represents the IC query as a sparse vector. So I had to, just for simplicity, just convert it into a straightforward vector. In fact, Zcash doesn't even, it's not really a sparse vector. All the elements are filled anyway. So this is the first bit here. And then finally, it calls into the Rust library here. So we're passing in all these pointers. In the case where we have a pointer to a variable length bit of memory, we have to pass in the length as well. And so we first run the Rust verifier, and if it fails, we failed verification, and then it falls back. And if it passes the Rust verifier, it'll try using the lib-SNARK verifier. Okay, so I did those changes, then I ran it. I had to run it with reindex on the daemon, and this took around 14 hours to actually re-verify the entire blockchain. That's about 160,000 blocks. So I'm just going to actually show you this working now, just so you can see it working. So that's my most recent change. I did some other changes actually to benchmark it as well, so you can actually see the times. So that's already compiled, so I'm just going to run that. You can see it running pretty quickly there in the background. Every so often it's verifying some proofs, so we can just shut that down now. So you can see there that the Rust verification time is only 0.117 or so, something like between 11 and 12. Sorry, yeah, between 0.11 and 0.12, and lib-SNARK is 0.08 to something like 0.09. So it's actually not too much slower, which sort of surprised me. I only ran these rudimentary benchmarks today, and even though this is a completely naive implementation of the verifier, it's actually only about something like 30% slower. So that's not too bad at all. Great. So, and then obviously we would need to check that it rejects invalid proofs. So I can just run a quick check for you now to show how I did this. I think in future I definitely need to add more tests and more special case tests and so on. So I'm just going to swap those two now. And rerun that. There we go. So it's failed. Presumably that was the first ever joint split, the first ever proof that appeared in the blockchain, and I think it seems to have failed verification, seeing as I swapped a couple of elements there in the proof. Check that it does actually return false on something. Okay, so I've already told you about the benchmarks there. It's not too bad as it's unoptimized and doesn't implement any of the additional optimizations in various recent papers and in lib-SNARK. So that, I guess that's one of the things I'd like to do next. Other things for future, handling points at infinity. So at the moment, this isn't really so much of a problem for me because the code calls into BN, which seems to handle points at infinity fine. But the issue with points at infinity is, my understanding is that they can't be represented as affine points. So you could potentially end up with some kind of error case. And if you get an error case, then maybe it would cause some kind of crash, and that could potentially be a denial of service vector. So we want to avoid these kind of error cases, and really just add tests for them to make sure that they are all handled properly. So Sean's written some explanations here, and he's also added some example tests. So it'd be nice to add that in. And as I've mentioned, I'd like to implement an optimized version and see how fast it can go. And the other thing that would be nice is really Sean Bow's been writing a new library for pairing cryptography called Pairing, and essentially he thinks that I should just implement or someone should just implement BN254 in the new library to take advantage of all the new stuff that he's been working on. So that would be a nice thing to do as well. And finally, I think the verifying key, because it's so short, ideally it should just be embedded at compile time. So that would be something nice to do. Okay, so thanks obviously to Sean Bow for all his help in pointing out various things, and obviously for writing BN in the first place, as this is mostly just a thin layer on top of BN. Please let me know if you have any questions. I can take questions now.
Cool. Thank you very much for that very detailed presentation. We did have a question. Well, first, I guess a clarifying question about the paper that you mentioned. Was that the zk-SNARK paper or the Zcash protocol spec that you're referencing?
Yeah, so the one I'm referencing, I've linked to it from the GitHub repo. It's the BTTV 2015 one.
Okay.
I don't know if you can share my screen again, but I'm looking at it now.
Yep. And we also had a question about, from Nathan actually, about your choice to use reindex instead of starting a new node. Was that to save bandwidth?
Yeah, I guess. It would be nice if there was a way to just run the verifier, but that was kind of the easiest way I could see to use an already downloaded blockchain and rerun it. So it would be nice if there was a way to only run the verifier and not have to do the reindexing, because the reindexing is additional performance cost.
Yeah. So I'm actually, we have a question from Sean himself. He said, regarding FFI boundary Boolean handling in the library, did you look at libc crate?
Libc
crate. I don't know the context here, so it could just be lost in translation.
Yeah, I'll ask him about that. No, I haven't. I don't think. I quickly
maybe he can clarify in the chat too,
okay.
And then I'll reread it.
Yeah.
But in the meantime, I was just curious about your kind of plans for like what would need to happen for the sapling upgrade and like changes to Zcash circuit.
Well,
would it have to be completely re-implemented, or?
Well, my understanding is that sapling itself, all the new stuff will be a completely separate new circuit, but obviously there'll need to be some kind of way to transition from the old circuit to the new one. So, the old the Sprout verifier will be needed, in the future. So potentially, I don't know if it would be of interest to run it, solely in Rust, or maybe run it simultaneously with the existing lib-SNARK verifier, depending on the discussion that goes on there. But yeah, this is. I mean, at the moment, this is more for me to learn how it works, really, because I find the best way to learn something is to kind of go away and build it. So
cool. Okay, so Sean says there is a Rust crate called libc, which contains intrinsics or something for handling booleans at FFI boundaries.
oh, great.
You might be able to just use that instead of doing that cast.
Yeah, I use libc. I use the libc uint8 type, but maybe there's something I missed there. Yeah, I'll look into that.
Okay. Have you seen Andrew Palestra's Rust Bitcoin? That might be a fun thing to poke at in this context, says Nathan.
Yeah, I've had a look at that, and also Parity have written, Parity Technologies, who kind of known more for their Ethereum work. They've written a completely, ground up implementation of Bitcoin in Rust as well. So they're both very interesting. Maybe something for Zcash to look into in the future.
Yeah. Yeah, I think our team is kind of all on board with Rust and like doing a transition in that direction. So that would be really exciting.
Yeah, I mean, quite aside from all the memory safety and the compile time checks, I think the thing I like about Rust as well is the tooling's quite nice. I think because it's all been written relatively recently, there's not so much of a divergence and so many different ways of doing things. So, there's a tool called Cargo for handling crates and dependencies and compilation and benchmarking and testing. So, all of these things are quite consistent, and they're quite enjoyable to use.
Great. I don't see any additional questions in the chat right now. I guess I'm curious if you've been involved in the Zcash community for a while now, which is great, and like we're all really thankful for a lot of the work that you've done. What interests you in Zcash, and like what are you kind of looking forward to in the development future roadmap?
Yeah, I mean, I guess I saw the original paper, I think the ZeroCoin one, a few years ago, and I was quite excited about it. And obviously it took quite a while to actually reach, to become reality. So it's been really exciting to watch it evolve. I think the thing with Sapling that's really cool is the fact that, I mean, there's so many great things coming with Sapling, but I think obviously the performance improvement is going to be really big, and I think that's really going to change things for people, because I think potentially one of the things that people sort of may have concerns with at the moment is the long proving time and potentially the memory usage, although that could probably be optimized. But I think Sapling is going to be quite drastically better than that. But there's also various other things coming, like the pay to verification key stuff sounds really cool. Yeah, there's so many different things in the pipeline. I'm also interested in implementing Bolt, which is kind of like a version of Lightning, but directed at Zcash. So yeah, I'm still trying to see how I can get involved with that.
Yeah, there seems to be a lot of, or at least a handful of people in the community that are building projects that are really looking forward to Bolt. So that would be cool to see kind of a rally around getting that going. I'm actually curious, you've only recently written this tool, and you have you have improvements planned for it, like optimization improvements. Do you also plan to do an external audit, kind of like going along with the theme you introduced?
Of the code that I've written?
Yeah.
Yeah, I think obviously for any of this to, I mean, if it was to be included in Zcash, it would need to be audited by experts. In particular, like, I think the code that I've written now is fairly simple, and I think it's kind of obvious that it's just a straightforward translation, but it would still need to be checked over by someone. But I think anything more complicated like implementing the BN254 curve in the pairing library would need to be audited by someone. So yeah, I mean,
cool.
I'm still learning, so this is all like an opportunity for me to learn about zk-SNARKs and learn about the various tricks that go on under the hood, which I'm quite interested in.
Do you so this is kind of like a personal project for you and a learning project for you. Do you, like, if someone were interested in helping, would you be interested in that? Like, is there anything kind of specific that you would kind of put someone towards, or any collaboration you'd be interested in?
I'm definitely open to people reviewing my code and any suggestions. I don't know if there's any specific tasks right now that I'd kind of pass on to someone, but I'll definitely, on the GitHub repo, I'll definitely start opening some issues as they come up. I mean, the main thing that I mentioned is I would like to implement the various optimizations, so it's not like a naive version. See how fast that runs, and then basically implement BN254 in the pairing library. So those are the kind of things that I've got planned. But also writing tests and that kind of thing would be useful.
Cool. Those are my questions that I had, and I don't see any new ones in the chat. Maybe you could kind of just give a shout out to the other kind of projects that you've worked on. So you did the Vanity address generator, right, for the shielded addresses?
Yes. Let's see. So this is a GPU-based vanity address generator for shielded addresses. So yeah, if you want to create a shielded address that starts with a particular prefix, it does case-insensitive matching as well. It'd be nice if someone could review the code, but I think it's fairly straightforward. The main code is here, which is the OpenCL. Hang on. Yeah, this is the OpenCL bit, which essentially just it's just an implementation of SHA-256 compress on the GPU, and it just runs it with a random seed and searches for and stops when it finds a match, basically.
Cool.
I'll also be curious. I mean, some people may not necessarily agree with vanity addresses in general. There may be reasons that they think they're bad, but I just thought it would be fun to try.
Yeah, it's been something that users have requested. Like, there are tools for the transparent addresses already that are just based off of ones that were made for Bitcoin.
Yeah.
So I think people are gonna use these kinds of things anyway. So having a tool for it is.
I mean, obviously,
useful.
there's a slight difference with Bitcoin in the sense that you're not really supposed to reuse addresses, whereas with Zcash, you have kind of, because of the way that protocol works, you can reuse an address. I mean, I don't know what the general guidance is on that, but clearly in the protocol, if you reuse an address, the privacy guarantees are much greater than Bitcoin. So, so potentially you might consider having, if you're a merchant or something that has some address that you want to put out publicly, you might want to generate a vanity address just because. Obviously the thing with vanity addresses is no one should ever just look at the prefix. You should always check the entire address because anyone else could probably generate an address with the same prefix.
Yeah, that's the one. That's the one risk.
That's the reason why people don't like vanity addresses, I think.
Yeah, exactly. Cool. Well, thanks for giving this demo and presentation. If you have any final words, you can shout them out now. Otherwise, people can follow up with you on the Rocket chat, which is chat.zcashcommunity.com.
Yes. So yeah, you can contact me. I'm on Twitter as Pluto Monkey, which is all my kind of cryptocurrency stuff, and I've got a website, plutomonkey.com, which is kind of still under construction. I have a lot of projects in the pipeline, but yeah, please get in touch. And if you have any questions, please contact me on Twitter or talk to me in the Rocket Chat. I'm at Jason Davis there. So
great, thank you so much, Jason. We're actually doing another show and tell in 2 weeks, and we're going to be demoing XCAT for y'all to see. So that should be really cool. We'll set up a live stream for that very soon. So thanks everyone for watching. See you next time.